Hi, welcome back everyone. In this video, we're going to be taking a look at several examples where we are going to write the equation for a line, or write what's called a linear equation. And like it says right here, in previous sections, we've graphed lines when we're given the line's equation. And now we're going to kind of do the opposite. We're going to look at either the line on a graph or some information about the line, and we are going to write the equation for that line. Now, first of all, I want to remind you that we've looked at two forms of linear equations. We've looked at what is called standard form, which is the ax plus by equals c form. And we've also looked at slope-intercept form. Slope-intercept form, remember, is y equals m times x plus b, where the a and the b and the c up here don't really stand for anything specific, but in slope-intercept form, the m is the slope and b is the y-intercept. And the first few examples we're going to take a look at are going to be probably pretty easy to write using slope-intercept form. And so when we're going to write a slope-intercept form equation, we need to know the slope and the y-intercept. And so sometimes, like in example 1, that information is just given to you straight away. You can see in example 1 we have an equation of a line with a slope of 3/4 and a y-intercept of -1. So this one's going to be pretty easy to write the equation for using slope-intercept form. We know that m, the slope, is 3/4, and we know right here this -1, that's going to be our b value. It's the y-intercept. So now all I have to do is take this 3/4 and this -1 and put them where they go in the y equals mx plus b. So y and x are going to stay as variables. You're going to see that continuously in all the examples I'll be looking at today. The y and the x stay in your equation as variables. You shouldn't be putting numbers in those for your final answer. But any of the other variables in kind of the generic form of the equation should end up with numbers in their places. So the m and the b in this case. So we take y equals, and then we put the 3/4 where the m is in this up here, and then we tack on the x, minus 1, because it's technically plus b, but we know that this would technically be y equals 3/4 x plus -1, but we don't usually like that look of plus -1, so instead of writing plus -1, we just write -1. So y equals 3/4 x minus 1 is your equation in example 1. And that's about as easy as it can get. Now in example 2, we'll see it's a little bit trickier. In example 2, we have an x-intercept of 3 and a y-intercept of 1. So first of all, we'll notice that that right there is going to be b. So we know this equation is going to be y equals something times x plus 1. What we don't know right now is m. We don't know the slope. But we can calculate the slope of this line pretty easily, because what we do know are two of the points on this line. We know it has an x-intercept of 3. Now remember, if I'm graphing a line, and so I got my x and y axis like this, and then maybe my line looks like that, the x-intercept is the place where that line is going to cross the y-axis, and the y-intercept is the place where that line is going to cross the y-axis, right? So whatever value at x is whatever the value is at x where that line crosses the x-axis, that's your x-intercept. But what we need to think about for this problem, since we're trying to find the slope of it, is we need to think what are the actual coordinates of the point where the line is crossing the x-axis. And we know it's going to be whatever the value is for x, comma, 0, because at that point where we're crossing the x-axis, we are going to be at 0 on the y-axis. So in this case, with an x value of 3 for the x-intercept, we know that point is 3, 0. And then we just kind of reverse that idea for the y-intercept. Wherever the y-intercept is, the x value is 0, and the y-intercept is whatever the number is for the y-intercept, right? So this would be 0, 1. So now we can just do the y1 minus y2 over x1 minus x2 formula to find the slope, right? This will give us our value of m. So y1 would be 0 minus y2, which is 1, over x1, which is 3, minus y2, x2, which is 0. So we have 0 minus 1, which is -1, over 3 minus 0, which is 3. So my slope here is -1 over 3. So that's my value of m. I just put that in front of the x, and now y equals negative 1/3 x plus 1. That would be my equation for this line in slope-intercept form. In example 3, what I'm giving you is I'm giving the actual picture of the line. So we want to write the equation. Now we're still thinking, right? We're still thinking about using y equals mx plus b form, where we just need to know the slope for m and the y-intercept for b. Well, those two things can actually be determined pretty easily looking at an equation on a graph, or looking at a line on a graph, right? Let's start with the y-intercept. That's the place where we're crossing the y-axis, or the vertical axis. So I look at that line, and I can see it's crossing the y-axis right there. So what value of y are we crossing at? That looks like a 4 to me, right? So our b value is 4. So I know my equation will be y equals something times x plus 4. So now I try to determine what my slope is. And remember, slope could be thought of like we did up here, y1 minus y2 over x1 minus x2. Or we can think of it as rise over run on a graph. So now I try and find another point where I can easily determine the rise over run. So I look at this point right here. That looks like a nice easy point to use, because that point looks like it's right at the crossroads of two of the grid lines on my graph here. In other words, it's a 3, 2. It doesn't have any fractions in its coordinates or anything like that. So if I look at rise over run to go from one point to the next, that should tell me what the slope is. Now I notice that this slope is going down from left and right. So I know this should end up being a negative slope if I calculate this rise over run correctly. Let's keep that in the back of our mind. Okay, so going from this point to this one, I'm going to go down 1, 2, right? I got to go down to this level from here, so that's a down 2 movement. And then I go over to the right 3 spaces, so that's a run of 3. So my rise, well, actually I went down, it was a negative, over my run, which was a positive movement because I was going to the right. Oops, I put negative 3 for the rise, that should have been negative 2. And my run was 3, so negative 2 over 3, or negative 2/3, that's my slope. So I put that in right here, negative 2/3, and my equation is set. It's y equals negative 2/3 x plus 4. So that's slope-intercept form, y equals mx plus b. And it's easy to do those kinds of equations when either you're given the slope and the y-intercept, or where those two things, both of them, can be pretty easily determined. In other cases, like when you're given the line's slope and some other point on the line, not the y-intercept, but some other point, or if you're given 2 points on the line and not given the slope, then a new form of an equation can be written. It's called point-slope form. And point-slope form looks like this. If your equation is passing through a point x1, y1, and has a slope of m, then point-slope form looks like this. Y minus y1 equals m times the quantity x minus x1. So the location of the point is used in this formula, as well as the slope. That's why it's called point-slope form, right? We're using one point and the slope on the line to write the equation. We put this, m is still the slope, so we put the slope out in front here. We take the x-coordinate of the point we know, and we subtract it from the variable x in our equation. And we do the same thing with the y-coordinate of the point that we know. We subtract it from y. So to give you a real quick example, look at example 4. I'm giving you the slope, right? We know that's going to be m. And I'm giving you a point this line goes through, 5, negative 2. So 5 will be x1 and negative 2 will be y1. So now the equation looks like this. Y minus y1, which is negative 2, equals m, which is negative 1, times x minus x1. Now we want to clean this up just a little bit maybe, because we have subtracting a negative here, and we know we can write that as y plus 2 instead of minus negative 2. And this negative sign, negative 1 out in front of this, parentheses doesn't actually need to be here. We can go ahead and distribute this in maybe. We can see negative 1 times x, which is negative x. Negative 1 times negative 5 will be positive 5. And if I wanted to, I could leave it like this. Y plus 2 equals negative x plus 5. This is a fine answer for the equation of this line. But if I wanted to take it one step further, I can make it look like the slope-intercept form where the y was isolated by itself. So I just subtract 2 on each side. y equals negative x plus 3. And this would be a fine answer, but this right here is also okay if you're writing the equation of a line. Now let's look at the next one. I'm given 2 points, right? Not the slope. But like we've kind of figured out already, I can figure out that slope pretty easy by doing y1 minus y2 over x1 minus x2. So that would be negative 1 minus 2, right? y1 minus y2 over 3 minus 2, because that's x1 minus x2. So that would be negative 3 over 1, which we can write it as a fraction, but we don't need to. We can just write that as negative 3 if we want. So we know now the slope, and we actually have 2 points that we can pick from. And just because we call this y1, or x1 and y1 when we were calculating the slope, we don't have to use this point when we're writing point slope form and using x1 and y1 and that. We could actually have picked this one. I'll go ahead and do that. I'll use this point in the answer that I'm going to give. So my equation will be y minus y1, which is 2, equals the slope, or negative 3, times x minus x1, which is also 2. And now I could leave it like this even, right? This is an okay answer if we're writing the equation of the line. I can do the distribution here if I wanted to. So I could say y minus 2 equals negative 3x plus 6. Negative 3 times negative 2 will give me positive 6. This is an okay answer. If I wanted to isolate the y, I just have to add 2 to both sides and say y equals negative 3x plus 8. Either one of these is fine. That answer is fine, that answer is fine, and that one's fine. It just depends on if you want to keep your answers consistent with the y isolated. If you want to take care of this distribution right here, you can. I don't really mind. Any of these would be fine because they are all considered equations of this line. Okay, one more thing we need to do. One more example. And it's this one. We have a line, and we're told that the equation of the line we're trying to write is going to be perpendicular to this one, and then it's going to pass through this point. Well, why does it matter if it's perpendicular? Remember, perpendicular lines have slopes that are opposite reciprocals. So if this line's slope is 3 over 1, then our slope will be the opposite sign, so that's a positive, so our slope will be a negative, and then the reciprocal, so we'll take that and flip it over. So it'll be negative 1 over 3. And then we have our x1 and y1 right here. So we can write our equation pretty easily. We'll say y minus y1, so y minus negative 7, equals m, or negative 1/3, times x minus x1, which is 6. And then I do like to kind of clean this up a little bit because this doesn't look very nice, doesn't look very kind of aesthetically appealing, this minus negative 7. So I'll write y plus 7 equals negative 1/3 times x minus 6. And you know what? I'm just going to leave it like that this time. I'm not going to bother with distributing this negative 1/3 into this parentheses. I'm just going to leave it like it is. So there's my answer. And there's the video that we have for, that was kind of an ugly box. Let's make that a little bit nicer. This is the video. This is it. This is the last one. So now you should know how to write the equation of a line, given some information about it. All right. Good luck, everyone.